Imagine you are falling. But you are not falling toward the ground. You are falling toward a point in space. There is no wind rushing past your ears, just the silent, relentless pull of an unseen force. This force, gravity, grows stronger with every passing moment, becoming more powerful than anything you have ever experienced. It is a one-way journey into the deepest known mystery of the universe. This is a black hole. It represents the ultimate victory of gravity, a cosmic phenomenon so intense that it captures everything, including the very fabric of light itself. The universe, in all its grandeur, has places where the rules we know are pushed to their absolute limits. Black holes are not cosmic vacuum cleaners, actively hunting for things to devour. They are simply regions of space-time where matter has been compressed into an impossibly small area, creating a gravitational field of unimaginable strength. Think of them as the natural, albeit extreme, endpoint for the most massive stars in our universe. When such a star runs out of fuel, it can no longer support its own immense weight. The core collapses under its own gravity, squeezing down until it becomes a black hole. This is not science fiction. This is the universe operating under its own laws. The name itself, black hole, is a beautifully descriptive piece of science poetry. It is here, at this precipice, that our exploration of what lies inside a black hole truly begins, at the point of no return. The first and most crucial concept we must grasp is the event horizon. This is not a physical surface you could touch or stand on. It is an invisible boundary, a perimeter of consequence. The simplest way to think about it is as a one-way door in space-time. Once you pass through the event horizon, you can never go back. All paths, for every piece of matter, every photon of light, lead inward toward the center. There are no paths that lead out. This is a fundamental rule dictated by the extreme curvature of space-time near the black hole, a cosmic law from which there is no appeal. Imagine a powerful, wide waterfall. As you float in a boat far upstream, you have control. You can paddle left, paddle right, paddle back to shore. But as you get closer, the current gets stronger. At some point, you cross a line where the water is moving faster than you could ever paddle. No matter how hard you struggle, the current will carry you over the edge. The event horizon is precisely like that line. Before you cross it, escape is possible if you have a powerful enough rocket. The instant you cross it, no engine, no force, no technology imaginable can propel you faster than space-time itself is falling inward. From your perspective, if you were falling into a supermassive black hole, crossing the event horizon might be surprisingly uneventful. You would not necessarily feel a jolt or see a visible wall. You could still see the universe of stars behind you, though their light would be increasingly distorted and warped. So, what happens after you cross the one-way door of the event horizon? Our current theories, specifically Einstein's theory of general relativity, point to one destination, the singularity. This is a word we use to describe a concept that strains the very limits of our imagination and our mathematics. A singularity is predicted to be the center of the black hole. Entire stars, vast clouds of gas, anything else are crushed into a region with zero volume and infinite density. Think of it as the ultimate cosmic compression point. It is crucial to understand what infinite density really means to a physicist. It's a sign our equations have broken down. General relativity describes gravity with incredible precision, from the orbit of Mercury to the bending of starlight. But inside a black hole, it gives answers like infinity, a clue the theory is incomplete. It's like a calculator flashing error. The math points to a concept, but it doesn't give a full physical picture. Visualize it. Space-time as a flat, flexible rubber sheet. Place a bowling ball on it. The sheet dips. Marbles roll and curve toward the dip. To make a black hole, press with a needlepoint so heavy it punctures the sheet. The puncture becomes a bottomless pit, the singularity at the very bottom where curvature goes infinite. The analogy breaks down. we can't conceive a true bottomless point. Falling toward the singularity would be the final destructive act. Gravity wouldn't be uniform as you fall. The part of your body closer to the singularity would be pulled much more strongly than the part farther away. That difference, tidal forces, would stretch you thinner and thinner, like a strand of spaghetti. Spaghettification. For small black holes, the stretching happens before the event horizon. For supermassive giants, you might cross intact, only to be stretched on the plunge toward the center. The idea of a singularity with infinite density is where our classical understanding of gravity, general relativity, hits a wall. To go further, scientists believe we need to bring in the other great pillar of modern physics, quantum mechanics. Quantum mechanics is the theory that governs the universe on the smallest possible scales. The world of atoms, electrons, photons. This theory is bizarre and counterintuitive, describing a world of probabilities and uncertainties. The problem is, general relativity and quantum mechanics do not currently work together. They are like two brilliant but conflicting instruction manuals for the universe. Inside a black hole, you have an immense amount of mass, the domain of general relativity, crushed into an incredibly tiny space, the domain of quantum mechanics. This is the one place in the modern universe where both theories must apply simultaneously. Therefore, to truly understand the singularity, we need a new, more complete theory that can unite them, a theory of quantum gravity. Physicists around the world are working on candidates for this theory, such as string theory and loop quantum gravity, but we are not there yet. What lies at the center of a black hole is not just a mystery, it is the key that could unlock the next revolution in physics. Some of these new ideas propose that the singularity is not an infinitely dense point after all. Instead of a singularity, there might be something else. For example, matter compressed to a state of maximum, but not infinite density. A Planck star, a fuzzball. In this view, the information that falls into the black hole is not destroyed in a singularity, but is stored in a complex quantum state. The black hole's interior would be less of a bottomless pit and more of a strange, hyperdense object governed by quantum rules we do not yet fully comprehend. Another fascinating, though highly speculative idea is that the singularity might be a gateway to another universe, a different region of our own space-time, forming a wormhole. While mathematically possible under certain exotic conditions in general relativity, there is no evidence that such structures are stable or could actually exist. These ideas highlight how little we know for certain. Since we cannot look directly inside a black hole, how do we know they even exist? We hunt for them indirectly by observing their powerful influence on their cosmic neighborhoods. Black holes are messy eaters. As matter, gas, dust, and even entire stars is drawn in by a black hole's immense gravity, it does not fall straight in. Instead, it spirals inward, forming a vast, flat, rotating structure called an accretion disk. The friction and compression within this disk heat the material to millions of degrees, causing it to glow fiercely across the electromagnetic spectrum, especially in X-rays. These glowing accretion disks are one of the brightest beacons we can detect. Our X-ray telescopes, orbiting high above Earth's atmosphere, can spot these intensely energetic signatures from across the universe. When we see a massive, compact source of X-rays in a location with no visible star to explain it, we have a strong suspect for a black hole. Furthermore, by observing the stars orbiting near this central point, we can measure their speed and trajectory. If we see stars whipping around an empty point in space at incredible velocities, we can use the laws of gravity to calculate the mass of the object they are orbiting. If the mass is enormous and confined to a tiny space, we have found a black hole. The most groundbreaking evidence came in 2019 when the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow. They did not photograph the black hole itself, but the silhouette it casts against the glowing gas behind it. The image shows a bright ring of light, the accretion disk, with a dark circle in the middle. That dark circle is the shadow of the event horizon, the region from which light cannot escape. The size and shape of this shadow match the predictions of Einstein's theory of general relativity with breathtaking accuracy, providing the most direct visual confirmation of black holes to date. Sometimes, a star ventures too close to a supermassive black hole and gets torn apart by its extreme tidal forces. This dramatic event, known as a tidal disruption event, creates a brilliant flare of light seen across the cosmos, a cosmic distress signal announcing the otherwise silent black hole. Beyond observing light, we now have an entirely new way to sense the universe: listening for gravitational waves. Predicted by Albert Einstein a century ago, these are ripples in the very fabric of space-time created by the most violent cosmic events. Imagine dropping two heavy stones into a still pond. The ripples they create spread outward, interfere with each other, and eventually reach the shore. In the same way, when two massive objects like black holes spiral toward each other and merge, they send powerful gravitational waves rushing across the universe at the speed of light. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by directly detecting these waves for the first time. The signal was the unmistakable chirp of two black holes, each about 30 times the mass of our Sun, merging into a single, larger black hole. This was not just a confirmation of Einstein's theory, it was the birth of gravitational wave astronomy. For the first time, we could hear the universe's silent symphonies, events that produce no light but shake space-time itself. This discovery opened a new window onto the cosmos. These gravitational waves carry a wealth of information. By analyzing the frequency and amplitude, scientists can determine the masses of the merging black holes, how fast they were spinning, and how much energy was released in the collision. The energy released in a single black hole merger can be greater than the light emitted by all the stars in the observable universe combined, yet it is released entirely as invisible gravitational radiation. These detections confirm that black holes exist in a wide range of sizes and merge far more frequently than we once thought. Each detected merger is like a sound recording of a black hole collision. While it does not show us what is inside the event horizon, it allows us to test the properties of the event horizon itself during the most dynamic process it can undergo. As the two black holes merge, their horizons warp, deform, and combine into a new, single horizon. The final ringdown emits gravitational waves that precisely match general relativity. Powerful evidence our exterior picture is right, even as the interior remains a profound mystery. So, what is inside a black hole? The honest, scientific answer is, we do not know for sure. We stand at the edge of our knowledge, peering into an abyss where our most trusted theories cease to function. We have strong clues and powerful mathematical pointers. Our journey has shown us three main ideas. The event horizon acts as a one-way boundary. General relativity predicts a central singularity where space-time breaks. Our observations from the outside, through light and gravitational waves, confirm the existence and behavior of these objects with stunning precision. But the interior remains shrouded in theoretical fog. This is not a failure of science, it is the very essence of it. Science is not a collection of final answers, but a continuous process of asking better questions. Black holes force us to ask the biggest questions of all. What is the ultimate nature of space, time, and gravity? What happens when matter is pushed to its absolute limit? Is information truly lost forever when it falls into a black hole, or does the universe have a way of preserving it? The quest to answer these questions drives physics forward, pushing us toward a deeper and more unified understanding of the cosmos. The universe is under no obligation to make sense to us. It is vast, strange, and filled with phenomena that challenge our everyday intuition. Black holes are perhaps the ultimate expression of this cosmic strangeness. They are not monsters, but natural, inevitable consequences of the laws of physics. They represent the boundary of our current understanding, a place where familiar rules give way to a new reality we are only beginning to imagine. To study them is to engage in one of the grandest adventures of the human intellect. So, the next time you look up at the night sky, remember it is filled with these silent, invisible giants, the ghosts of massive stars, the anchors of galaxies, the keepers of the universe's most profound secrets. We may never be able to send a probe inside one, but through the power of mathematics, observation, and sheer curiosity, we will continue to chip away at the mystery. The journey to understand what lies inside a black hole is a journey to the very edge of reality, and it has only just begun. The cosmos awaits. If this blew your mind, please like, subscribe, and ring the bell for more cosmic wonders.